The resistance of a conductor is defined as the ratio of the potential difference across the conductor to the current in the conductor. And the formula for this electrical resistance is written like this, where R, the resistance, is equal to the voltage divided by the current. And the resistance has units of ohms, represented by the capitalized omega symbol here. So let's explain what this means in more detail. Let's imagine we have two different metals and we want to measure their electrical resistance. If we obtain two materials with exactly the same size and dimensions and connect them up to a circuit with a 5-volt power supply, we can find the resistance of both these materials individually. Now, because no other device or material is connected to this circuit, we know that the voltage drop across both the iron and gold material here is going to be 5 volts. The current, however, is going to be different for each circuit. And remember, the electrical current is a measure of how much charge can pass a point in this circuit per unit time. The more charged particles moving through a point every second, the higher the current will be. So let me ask you a question. If I told you that the iron material here has a higher resistance than the gold, could you tell me which circuit will show the highest current flow on the ammeter? And remember, both the metal bars, the iron and the gold, have the same dimensions and are at the same temperature. Now, this is important because the temperature and the dimension of the material can affect the resistance, and we'll get into that in a future lesson. Well, resistance is a measure of how much a material opposes the flow of electrical charge, and therefore the current. If we rearrange the equation that we wrote at the beginning of this lesson and make the current the subject of the formula, the current is equal to the voltage divided by the resistance. Now we know the voltage drop is constant here, but the resistance value can change depending on the material or the device we put in the circuit. We can see from our formula here that if the resistance increases, the electrical current will decrease. Let's say that the resistance reading is lower. In this case, the current in the circuit will increase. So because we said that iron has a higher resistance than gold, this must mean that the iron with a higher resistance will restrict the current flow more than that of the gold, so long as both these materials have the same dimensions and are at the same temperature. So the current reading on our ammeter in circuit 2 should be lower, because the iron has restricted the flow of charge more effectively. So let's try this question. The current in an electrical immersion heater is 6.3 amps, when the potential difference across it is 12 volts. Calculate the resistance of the heater. So I've drawn a little diagram here showing the immersion heater in some water, heating up the water. Now the heater itself is acting as a resistor, and as it resists the flow of current moving through the circuit, the resistor also heats up, and this energy is being used to heat up the water. So all we need to do is use our resistance formula and plug in the values. So we got 12 volts for the power supply, and we know the current moving through the circuit is 6.3 amps because we measured it on the ammeter. So that must mean that the immersion heater's resistance is 1.9 ohms. So now let's say we've been given a simple electronics project in class. Our goal in this project is to create a circuit that will light up an LED or light emitting diode when it's attached to a 5-volt battery supply. So effectively we're just creating a flashlight here. But we're also warned that if we attach the LED directly to the power supply or the 5-volt battery, it will destroy the LED. And if that happens, we fail the assignment. Now our teacher has helped us out a bit and told us that we can use a resistor in the circuit to ensure that the LED isn't overwhelmed by electrical current. So we've got the 5-volt battery supply at the bottom here, and the current moves clockwise through the circuit. And in parallel to the LED, we've set up a voltmeter, and we've also put an ammeter in the circuit here. Now with this specific LED here, it needs to have a voltage drop of 2 volts for it to function properly. And it cannot handle a current higher than 20 milliamps. Anything higher than 20 milliamps is going to destroy the LED. With this information, can you tell me the minimum resistance required for our resistor? So the first thing you need to know about electric circuits is that the sum of all the voltage drops across all devices must equal the potential difference of the power supply, where all devices are attached in series, so the resistor and the LED. And we can draw a little graph here where on the y-axis we've got the voltage or the potential difference at some point in the circuit, and on the x-axis on the left-hand side we got the position of the positive plate or the positive terminal of the battery, and on the far right hand side that's the location of the negative part of the battery, the negative terminal. So as soon as we hit the resistor, we get a drop in potential difference, and the same is true with the LED as well. And the voltage after the LED should be 0 volts so long as the wires have 0 resistance. So we know that the LED has a potential drop of 2 volts. This must mean that the resistor must have a potential difference of 3 volts. 3 volts plus 2 volts equals 5 volts. Okay, so we know the difference in voltage before and after the resistor, which is a difference in 3 volts. We now need to choose a resistor with a resistance high enough to reduce the circuit's current to 0.020 amps or 20 milliamps. How can we do this? So again, we can use our equation, resistance is equal to the voltage divided by the current, to find what suitable resistance we need for our resistor. So we know what the voltage drop is across our resistor, which is 3 volts. And we need the electrical current to be 20 milliamps. So with this information, the minimum resistance we must have for our resistor is 150 ohms. And if we were building this circuit, we'd find the suitable resistor closest to 150 ohms. And if we don't find a resistor that's exactly 150 ohms, we would have to choose a resistor that's the next highest value.